So in this section, we're now going to take our double integrals up another notch and talk about triple integrals. And so really what we're going to focus on in this section is just kind of doing some examples of setting things up. We'll do a couple examples of a triple integrals, but we'll mostly focus on how to do the order of the bounds and how to figure out the functions that each variable is changing between. Because our next couple sections after this are going to have a ton of examples where we're going to set something up in rectangular coordinates, but then we're also going to learn different coordinate systems. So we'll extend the concept of polar coordinates to 3 dimensions, which is cylindrical coordinates, and then we're introducing a new coordinate system, which is spherical coordinates. So what's going on here if we have a triple integral? Instead of having some surface that you're finding a function of or under, this can represent something completely different. So instead of having a region in an xy plane, you're really having a 3-dimensional object that's dictating what your bounds are going to be. So now we no longer call it a region R, we have some surface or solid E in 3 dimensions that tells us the bounds. So maybe our surface is something funky. Maybe it has like a sphere-ish shape on the top. But then it can do really whatever it wants. Maybe it kind of looks like a drooping, like ice cream scoop. Okay. So this is our surface E. So the triple integral of some function, which depends on 3 variables, potentially x, y, and z, over a general region E in R3 is, you have 3 integrals now, your function on the inside, and now instead of dA, it's dV, so it's a natural next extension. Your region E will dictate the bounds, and your dV can be really any order you want. With 2 variables, you had dy dx or dx dy. Here you have a lot more. You actually have 6 possible options for what dV could equal. So it could be just in order dx, dy, dz. But again, you can rearrange this in 6 possible options. Now, in terms of what this actually represents, it depends on the inside function itself. So if the inside function is 1, all that's really doing is find the volume of that shape. Okay? If the inside function is something like a density function, then this triple integral might find its mass. If you're taking physics, you'll see these have connections with finding moments of objects. And then we'll also see some extensions when we get to our next unit on vector calculus. So that's kind of a big application, and these integrals can be turned into double or triple. And they might represent something like the volume of fluid moving over an object in some kind of fluid field. Okay? So just kind of reiterate what I said. If this inside function is really just 1, then the volume of E is given by this triple integral. The reason for that is, well, this inside integral, if you do the order dz dx dy or dz dy dx, these z bounds would be exactly the thing that goes inside the function. Because when you would find the first antiderivative, and then it would be just z evaluated from those bounds, and those bounds would be exactly what we did in our prior sections to find what we integrated over. Okay. So let's start with a nice example. And using triple integrals, we're going to prove that the volume of a box with dimensions L, W, and H is our standard volume. length times width times height. So I'm going to start by drawing our box in 3 dimensions, and then we're going to set up our triple integral to find its volume. And again, technically you can do this with a double integral as well. But let's say in our x direction is that distance L, in the y direction is the distance of W, and then it makes the most sense for the height to be on the z axis. So these would be a couple of the corners of that box. And then just extending stuff out. Try to make this as nice as I possibly can. Trying to draw all of them to be parallel to whatever coordinate axis I'm working with. And then we've got the front of the box over here. Not too bad. And then you can go sketch in the back if you want, but it lies on those coordinate axes, so can't quite see it anyway. So this is our solid E that we're going to integrate over. So if I want to set this up with a triple integral, it's a triple integral over E, and on the inside we put a 1. Okay. Now from here, the order of the bounds doesn't matter because rectangular regions we know tend to have constant bounds. So when I have a third dimension, nothing else is going to change. So I'm going to give myself some space though to be able to put those bounds. And for this order, let's do dz, dy, dx. So if we start with the z bounds, that's the first or innermost integral. In this case, our z, regardless of the x and y we pick, starts in the xy plane, so it starts at 0, and it goes up to the plane z equals h. So my bounds here will be from 0 to h. Moving on to y, well again, y is always going to start back here at 0 and go to the rightmost plane, which is y equals w. So y changes between 0 and w. And then last but not least, we have x. X is always going to start at 0 and it goes out to the length. And then really from here, this integral is separable because this inside function doesn't have any variables. So just like we could with double integrals, we can split this and just multiply the product. So we've got the integral from 0 to L of dx. We've got the integral from 0 to W of dy. And then 0 to h for dz. And then luckily, each of these have a very simple antiderivative. The first one has an antiderivative of x, and you evaluate that from 0 to L. So that gives us exactly L. Antiderivative of this is y, evaluated from 0 to W. So we get W. And then antiderivative of this is z, evaluated from 0 to h. So we get exactly the volume, length times width times height. The only difference is if you were to do a double integral, just to show you the setup for that, you would set up a double integral and then you could do dy dx. You would still have constant bounds because it is a rectangular region of integration. So your y would change between 0 and w, your x would change between 0 and L. The only difference is the inside function. For that, we'd have to integrate over the height of this thing. And so in this case, that plane is z equals h. So the inside would just be h instead. But again, you can really pop that constant out. And then my L disappeared. You'd have from 0 to L, 0 to W of dy dx. And in the same way over here, it would split, and then you'd get the same exact answer. So there is that connection between double and triple integrals when you're finding volume. Okay? But again, a lot of times we're not finding volume. So now instead, let's go ahead and talk about what if we have a general region that we're integrating over and we have an arbitrary function on the inside. So in the same way as our double integrals, it was representing a volume, this still might have a physical meaning even with a function on the inside. You should always be getting numbers as your answer, never variables in here. This is representing some physical quantity. So what I want to do is I want to make sure that I'm setting up my bounds so that I'm not introducing a variable when I go ahead and plug those bounds in. So really, we kind of have to work from the inside out to figure out which variables can be in the bounds. So in general, the region E might not be a box. And it typically will not be a box. Instead, it can have more complicated bounds. So for example, we can have functions like the following. So if I want to calculate this triple integral over the region E with some function, and then integrated with respect to x, y, and z. I'm going to give myself lots of room here. And I'm going to set up my order of integration first. So let's say we do dz, dy, dx. Okay. The x can only have constant bounds because that is the last thing I'm going to evaluate. So these bounds will only be constants. When I'm integrating with respect to y, I do not want to introduce z because I've already integrated with respect to z. So really y can only depend on the variable after it because we haven't done that integration yet. So this can be a function, let's call it g1 of x up to g2 of x. But I can only have x in this bounds because I haven't done that integration yet. When I do dz, it can depend on y and x because I have not integrated either of those. So my innermost one can depend on the other variables. So here I can have something h1 of y and x. And let's do it in the correct order. And then same thing up here. This function can depend on x and y. If I want to do a different order of integration, maybe let's say we do y first, then z, then x. You can start from the inside this time. Well, y, because that's the first integral I'm doing, none of these bounds should contain y at all. So I can have one function up here, one function at the bottom, and it can depend on two variables. The two variables it can depend on are the ones I have not integrated with respect to yet. So in this case, this can be a function of x and z. This can be a function of x and z. Moving on to the middle piece, that can only depend on x. So here, this can be a function of x. This can be a function of x. That should be g2. And then the last bound, always the nicest, it's some constants. And let's do one more for good measure. Let's say we do dx, dy, dz. My inside x can depend on either of these. So this is a function of y and z potentially. And same thing up here. Then y can only depend on z. So this will be a function of z to a function of z. And then the end is still always going to be constant bounds. Now this is only 3 of them, so really I'm going to add in or vice versa down here because you technically have 3 more possibilities again. I just did one example with each of these variables at the start. But what I can do is I can flip these, I can flip these, I can flip these to give me those 6 possible ways to set this up. Okay. Now in your homework, you're going to have to figure out, you might just have to try things. You might set something up, and then when you try to integrate it, you can see it can be a little difficult. In that case, try switching stuff around. I will try on certain examples to prompt you which one is going to be the easiest though. So what I want to do before I get into setting up bounds is let's just do an example of a triple integral. Then we're going to go ahead and we're going to do one example. We'll go through it completely, and then I'll show you how you can set it up in like 2 different versions instead, so you can see how the bounds will work. So for this example, let's evaluate the integral I, which is a triple integral. The inside function is z sine of x dy dz dx. The bounds are 0 to the square root of 4 minus z squared, then from 0 to 2, and 0 to pi. So even though this inside separates, I can't separate yet because I don't have all constant bounds. I need to actually go through this first integral. So we can go ahead and take the first antiderivative at least. This has absolutely nothing to do with y, so its antiderivative is y times z times sine of x. And then this gets evaluated from 0 to the square root of 4 minus z squared. And again, I'm going to indicate this was y that we integrated with respect to, so we're going to plug this in for y. And then our order has not changed at all. So plugging in those bounds, thankfully, will give us just the square root of 4 minus z squared times z times sine of x. Because when you plug in 0, it is just going to subtract 0. Now at this point, I do have a separable expression with constant bounds. So my z is the first one, so those bounds are 0 to 2. And then we've got sine of x, which is the outermost integral, so those bounds are 0 to pi. So I can go ahead and break this down because I have constant bounds and a separable function. So that's sine of x dx. And then the integral from 0 to 2, I'm going to just put that z in the front so it's not as gross looking, 4 minus z squared. First one, we can just go through real quick. Antiderivative of sine is negative cosine of x, evaluated from 0 to pi. And that gives you negative cosine of pi, which is negative 1, and then minus cosine of 0, which is minus negative cosine of 0, so it's minus negative 1. That really gives you 1 plus 1, so the first piece just becomes 2. When I want to go through this expression, this is going to be a u sub because I have z squared inside the radical. That z will get sucked into that du. So we're going to make the substitution that u is the expression under the radical. So du is negative 2z dz. I don't have that negative 2, but that's not a problem. Negative 1/2 du is z dz. Now I also want to change my limits simultaneously so I don't have to go back. When z is equal to 0, u is equal to 4 minus 0 squared, so u is equal to 4. When z equals 2, u is 4 minus 2 squared, giving you 0. So this becomes negative 1/2. You got to be careful because the lower bound is 4, the upper bound is 0. And then we get square root of u du. And you can integrate it like this. You don't have to worry. You just plug in 0 first, subtract plugging in 4. I know it's backwards or non-conventional for what you're used to, but one thing you can also do is remember you can flip that order of integration because of this minus sign. It will flip these bounds. So it's really 1/2 from 0 to 4 of square root of u du. Now finding that antiderivative, that's 1/2. Add a power, or add 1 into the power, gives you 3/2. Divide by 3/2, same thing as multiplying by 2/3, and then evaluating from 0 to 4. And really, the 2's end up canceling, so that's nice. This becomes 1/3, and then we get 4 to the 3/2 minus 0 to the 3/2. And this you can simplify because this half power is saying take a square root of 4, so that's 2, and then 2 to the 3rd will end up equaling 8. So this becomes 2 times 8 over 3, or overall, this thing is equal to 16 over 3. So from here, I really just have one more example because, again, we're going to get more practice with this in our next couple sections as well, working with setting up bounds. So all I want to do for the remainder is we're going to find the volume of a solid in the first octant. We're going to do it one order of integration, and then I'll go ahead and show you how you would set it up with the other two. So for our last example, we're going to find the volume of the tetrahedron bounded by the plane (2x plus 4y plus z equals 4) in the first octant. So if you don't know what a tetrahedron is, it's really just kind of a shape that has 4 sides. In this case, it kind of looks like a little bit of a dice, but not quite. You can kind of think of a D4 as a tetrahedron. So if I want to graph this, because I'm definitely going to need to figure out my bounds, if I were to graph this plane, basically I want to see where it intersects all of the coordinate axes, because I'm really just looking in that first octant. I know it's going to be a shape like this, but what does that intersection look like just in octant 1? So if I set first x and y equal to 0, immediately that tells me that my z value has to equal 4. So when I go to graph this, I need to go out 4 in z's direction, and it would intersect this axis right here. Now if I set, say, let's do y and z equal to 0, that just gives me 2x equals 4. So it will intersect my x coordinate axis at x equals 2, which is right here. That one's 4, that one's 2. And then if I set x and z equal to 0, that just leaves me with y, but I have a 4 out front. So it tells me it intersects my y-axis at 1. So my plane passes through all of these points, and I'm only concerned with the first quadrant. So I'm really looking at this shape here. And I want the volume of the solid bounded by this in the first octant. So I really have this shape going on. This is our solid E. Okay. So you can set this up really any of the ways. It's not going to be bad. There's definitely one way that's better than the other, just because it saves you fractions. So the main thing is you would definitely have to solve this plane for one of the variables, and because that's going to be your first integral that you go through. You're always going to start at 0 and go out to that plane or that equation of the plane, which is 2x plus 4y plus z equals 4. Because of that, the easiest variable to solve for is z, because I don't have any constant in front of it. If I go to solve for x or y, I'm going to have to divide by 2 or divide by 4. And that's going to introduce fractions that I don't really want to do. At this point, yes, it's not too bad to deal with, but I still don't want to if I don't have to. So in this case, I'm going to solve for z, and you get 4 minus 2x minus 4y. So let's set this up in the order where I'm integrating with respect to z first, because I'm always going to start at 0 and go to the equation of the plane. So my z bounds are going to be exactly that, 0 to 4 minus 2x minus 4y. So for the other two, doesn't really matter a ton, but for sake, let's do dx dy. Okay, so starting with z, then integrating with respect to x and y. So if I want the volume, it is the triple integral over this region E. And in this case, we're going to use the bounds dz, dx, dy. So again, regardless of the x and y point you pick in, which is somewhere down here, you're always going to start at the bottom of the shape, which is 0, and you're going up to the plane. Okay. So here, regardless of the xy point, z starts at 0 and goes up to the plane. Which is the equation z equals 4 minus 2x minus 4y. So these will be the z bounds. What I need then are the x and y bounds, and that's determined by what's happening in the xy plane. So I'm going to zoom in just on that xy region now. So to find bounds on x and y, look at what's happening in the xy plane. So if you remember the points we found, x goes out a distance of 2, y goes out a distance of 1. And we have the line connecting them. So this is the bottom of that tetrahedron. Okay. If you want to figure out the equation line, you absolutely could do that because you have the y-intercept, which is 1. You have the slope, which is really negative 1/2. You can come up with the equation that way. But also what you can do is because you're on this plane, z is equal to 0. So if you do that with this equation, then you would get that 2x plus 4y equals 4. And because of our order of integration, we're doing x first, then y. So y is going to have the constant bounds, which are 0 to 1. So I need to figure out what is x changing between. So for that, regardless of the y value you pick, your x is always starting at 0, and it's going to the equation of this line. So I need to rearrange this equation to get it x in terms of y, because remember, the bounds on this can only depend on the variable we haven't integrated with respect to. So solving this equation, that would give us 2x is equal to 4 minus 4y, or x is equal to 2 minus 2y. Okay. And then just for completeness sake, I'll solve this for y because we're going to set this up another way as well. If you were to go about the order dy dx, you would have to manipulate for y. And again, the slope of this is negative 1/2, and the y-intercept is 1. Okay. But this is the equation that we want to utilize for the x bounds. So here, x will start at 0. And go to the line x equals 2 minus 2y, while the y varies between 0 and 1. So we finally have all of the bounds set up. We now can go ahead and find the volume of the solid. We have a triple integral, going to save lots of rooms. The inside is 1, and the order we picked is dz, dy, dx. So z starts at 0 and goes to that plane, which is 4 minus 2x minus 4y. Our x starts at 0 and goes to the equation of the line. So the upper bound is 2 minus 2y. And so again, z can have these variables in the bounds. X can only have y in the bounds. And then y has to be constants. And the constants y changes between are 0 to 1. Okay. So we are set up now. We just need to go ahead and evaluate this triple integral. So that's from 0 to 1, 0 to 2 minus 2y. Antiderivative, the inside is z, and evaluated from 0 to 4 minus 2x minus 4y. And luckily, when we plug in that lower bound, nothing happens. So really, we just get 4 minus 2x minus 4y inside here. And this is exactly what we did in the last section, because you had to figure out the function that went on the inside for your double integral. You use the xy planes to figure out your x and y bounds. But back up here, your z bounds would be starting at 0 and going up to the plane. So the inside expression would be the plane. So this is how we would set this up with a double integral. Okay. All right. So we are now good to go. We can integrate this thing with respect to x. So antiderivative of the first piece, we'll introduce an x. This will become x squared. We divide by 2, which is nice, and then that just introduces an x. So antiderivative is 4x minus x squared minus 4xy, and evaluated from 0 to 2 minus 2y. And again, this is what we're replacing x by, because we still need to integrate with respect to y afterwards. So we've got some algebra we're going to have to do to be able to integrate this. And again, luckily when we plug in that lower bound, it's just going to disappear completely. So we get 4 times 2 minus 2y minus 2 minus 2y squared minus 4 times 2 minus 2y times y, and then integrated with respect to y. So I need to go through and I need to expand all of this out because there's no way I can integrate it otherwise. First piece, thankfully, is just distribution, 8 minus 8y. Before I go ahead and subtract, I've got to FOIL this thing. So you get the first term squared minus 2 times the cross product of those two, 2 and 2y. And then the last term squared is positive 4y squared. And then distributing both the negative 4 and the positive y, that gives us minus 8y and then plus 8y squared. Okay. Now we got to see, does stuff clean up? And thankfully it does. We have minus 8y. So these two end up canceling each other out. Now grouping my like pieces, this is 8 minus 4. Those are my only constants. So that becomes 4. Then we've got negative 4y squared plus 8y squared. So that becomes plus 4y squared. And then this is our remaining y term, so we have minus 8y. And you can put this in order if you want, but not necessary because we're just going to integrate and evaluate this. So it is just a polynomial, so the antiderivative is 4y plus 4/3 y cubed, and then that would be 8y squared over 2, so minus 4y squared, evaluated from 0 to 1. If you plug in 1, that's 4, plus 4/3 minus 4. When you plug in 0, it all disappears. So the volume of this solid is 4/3. Okay? So this is one way we can go about the problem. Again, I'm going to show you how to do different bounds, but we're not going to actually go through those integrals because they're all going to be very similar to each other and just require a little bit of algebra. So I'm going to set this up in 2 more different ways. If you want some extra practice, we've done 3 of the versions. You could find the other 3, and then you could use something like Wolfram Alpha to figure out if you do end up getting 4/3 for that integral, just to kind of check yourself. But we're going to set this up using x first, and then we'll do dy dz and also dz dy. So we'll see both of those ways. So instead, let's set up this integral using dv being dx, dy, dz. So I'm going to start by just drawing our tetrahedron again, because at least this isn't so bad. Z goes up 4, y goes out 1, and then x goes out 2. Okay. So in this case, I'm going to start with my x bounds, because here you're going to have freedom for y and z, which is this triangle back here. And you're always going to start at that edge, which is in the YZ plane, and you're going to go out to the plane itself. So I need to solve this equation of the plane for x. So we've got to first subtract the y and z pieces, and then we need to divide by 2. And you can already see why this is not the ideal setup, because I'm going to have a 1/2 at my bounds. So my x bounds are going to start at 0, and they're going to go to this plane. Okay. Now I want to figure out what's happening in the YZ. And for that, I'm going to need to look at what's going on in the YZ plane. And the order I want to do is dy dz. So z is the last bound. So it doesn't matter which one you put where, but I'm going to go ahead and put it like this because yz is already in that flat surface back. So my z starts at 4, my y goes to 1, and then you have a line connecting these 2 points. And this is the back of that tetrahedron. So your z bounds are the nicest. That's 0 to 4, because that's the last thing that we end up going through. So I need to find y bounds, and z bounds are just the constants. So based on the z we pick, which I'll just pick these 3 z values, your y is always going to start at 0, and it's going to go to this line. And again, if I want the equation of line, I can use my slope-intercept form. However, it is again that edge of the plane that's hitting that part. So instead, I'm just going to set x equal to 0. So this line would be 4y plus z equals 4. My y bounds can have z as a variable, so I need to solve this for y, which is not pretty. It has 1/4 as a fraction. So my y bounds go from 0 to 1 minus 1/4 z. Okay. So if I want to set up the volume of the solid in this order, give myself lots of room. We're doing the order dx, dy, dz. My z bounds are 0 to 4. Y bounds are 0 to 1 minus 1/4 z. And x is 0 to 2 minus 2y minus 1/2 z. And it's a good habit to just double check that your bounds make sense. So again, starting with x, it can depend on y and z, and that's great. I have y and z in my bounds here, but I don't have an x. Y can only have this remaining variable z, and it does. So if I saw a y or an x at this point, I know I definitely set it up wrong because we've already taken care of the x variable. And then z again should be constant bounds. So you could go through this integral, go through the algebra, but again, it ends up leading to exactly the same answer. So now let's do the same thing, but let's go ahead and just flip this particular order. So instead of now this order, we're going to use dv is dx, dz, dy. So absolutely nothing is going to change with the x bounds. It's just the y and z. So to reiterate, just to show you one more time, we've got our tetrahedron, and because I'm doing x first, I'm concerned with what's happening in the YZ plane. If you did y first, then you would be concerned with the triangle over here in the XZ plane. So if I want to go ahead and find my x bounds, it's always going to start in the YZ plane and go out to the edge of this plane. So this is the equation. If I solve for x, we'd have to subtract all of those things and divide by 2. And we just did that. It's 2 minus 2y minus a half z. So the x bounds are still the same, 0 to this plane. Now I want to figure out my bounds using the order dz, dy. So again, drawing what's going on in the YZ plane. My z goes to 4, my y goes to 1. And this is that one side of the tetrahedron. We need z bounds, and then we need the y bounds last. And that's easiest. The constants that y changes between are 0 to 1. So in this case, what I do is I pick my y variable, and that will tell me what z changes between. And regardless in the figure, regardless of the y, it starts at 0, and it's going to go up to this line. So my lower bound is still 0, and I need the equation of that line. But again, just setting x to be 0, we get this. Because I haven't run through y yet, my z bound can depend on y, so I need to solve for z, which is at least a little bit nicer. It would be 4 minus 4y. So that is my ending bound here. So we have all the bounds we need. The volume of this solid is again a triple integral. And then based on the order we're picking, dx, dz, dy. X is changing between 0 and the plane. 2 minus 2y minus a half z. Z changes between 0 and 4 minus 4y. And y changes between 0 and 1. So just checking again, our bounds make sense. X can have y and z in the bounds. And great, it does not contain the variable x. Z should only depend on y, not on x, because we've run through that. And so the z bounds indeed do change, you're just dealing with y. And then my one bound dropped over here. I guess I hit undo by accident. y changes between the constant 0 and 1. Okay. So you can try setting this up the other three ways if you want. You could do dy and then those two options after it. And you could also do the other form for dz. You could plug these into Wolfram Alpha to verify you get the same value for each of them, but it is good practice. Just make sure you can set this up in a couple different ways. And you can see the benefit of one over the other because these two that we did involve some fractions as a bounds. And if we can avoid that, fantastic.